So welcome students. Today we'll be talking about some of the operators that MATLAB provides for dealing with scalar quantities. We'll also revisit how to define scalar variables. So as in our previous class, let's declare a variable x equal to 7. Without using a terminator, it echoes the result back, and we also declare a variable y equal to 8. I'll use a terminator here so that does not echo back. So if I want to see the value of x, I'll type x and enter. It will show me the value of x. If I want to see the value of y, I'll type y and enter, and it shows me the value of y. Now, some of the basic operators that are available in MATLAB include the addition, like x plus y gives the answer 15. Also is a temporary variable where MATLAB stores its intermediate results. You can use a third variable. Let's suppose z is equal to x plus y, so z will contain the value 15. Now besides addition, we also have subtraction, so x minus y yields -1, simple to understand. Similarly, x multiplied by y yields 56. Again, you can store these values in intermediate variables. Now we also have an operator named the power, raised to power. So x power to raised to power to y. This cap here represents the raised to the power operator. So x raised to the power y, y raised to the power x. So it gives us that particular value back. Now the other operator that we are using, that we'll be using, is division. We have two divisions in MATLAB. One is a forward division, or the right division. One is a left division. So if I write 5 divided by 2, it yields 2.5. However, if I write 5 left division by 2, it yields 0.4. What basically happens is when we write 5 divided by 2, the right division 5 will be divided by 2, so it yields 2.5. So it yields 2.5 here. However, when I write 5 left division by 2, it divides this 2 by 5. So 2 divided by 5 is 0.4. So that's what we get here. We'll talk about the right division and the left division later when we talk about vectors and matrices. They have a different meaning over there, and we'll defer that discussion to the later stage. Now, in the earlier class, I've also talked about some scalar functions. We'll revisit some of them. We have rem. Rem is gives the remainder of the division. So if I divide 5 by 2, okay, it has two parameters, the dividend and the divisor, and it returns back the remainder. So the remainder here in this case, as you can see, is 1, 5 divided by 2. So you do not have a modulo here. This percent sign does not represent the modulus operator. It represents a comment. So if you when we'll write when we'll be talking about scripts, we'll talk about this percent sign being used as a comment. We'll talk about that later. So again, another division. In order to see the remainder, we can write rem of 6 and 3. So the remainder here in this case should be 0. So it's simple to understand. Now there are other functions like round. It simply rounds the fraction. So 0.345. So it rounds it to an integer, to the nearest integer. So 0. So if I write a round of 0.5, it should yield 1. Okay, I hope you know how a round operation works. Now You can also use round in this way. You specify a fraction, let's suppose 0.4345, and you can specify the number of decimal places up to which this function should round the value. So if I write 2 here, it yields 0.35. So if you look at the values earlier, the value was 0.345, and I said MATLAB to round this value to 2 decimal places. So it rounded it to 0.35. You can see this 5 would be converted to 10, and the 1 would be given to this 4, and this 4 here becomes 5. So you can, let's suppose if I write this value 0.3452 and round it to 3 decimal places, the obvious value it should return is 0.345, because this 2 here is not significant, it's not greater than 5. So it yields 0.345. The 2 here is truncated. So this is simple, how this round function works. The floor and the ceiling functions, I've already talked about that. You can use any of the operators along with these functions, like z is equal to let's talk about another function, which is ABS, the absolute function. ABS of -3 is 3. Okay, similarly ABS of -3.5 is 3.5, and so on and so forth. So you can use these functions and create expressions as you want. Z is equal to x plus ABS of -3 plus let's suppose 5 to the power of 2. Okay, so I hope you know how the precedence of these operations works, as it's similar to the to other programming languages. So first this power will be evaluated, then other expressions like multiplication, division, followed by addition and subtraction. So now, having talked about these scalar values, and some of these scalar functions, let's start with declaring certain vectors. So I'll clear this command window here. Now, in order to declare or design, create a vector, you use the same syntax. You name a variable. Let's suppose x is equal to. In order to declare a vector, we use the square brackets, and we specify all the values that should be contained in that vector. So let's suppose x contains 2, 3, 4, 5. So these are four elements that are present in x. If I press enter, it echoes back the contents of x, says 2, 3, 4, and 5 are belong to this x. Now you can also use commas here. It's preferred that you use commas while declaring a vector, so it yields the same result. Now, in order to access the values of a vector, you use parentheses. So if I want to see which value is at position number 2 of x, or let's talk about position number 1 of x, so it gives me 2. It means that the indices for accessing values in vectors in MATLAB start from 1. So if I write x of 0, it should give me an error. So indices, it says that indices should be positive integers or logical values. So the indices start from 1 and go on up to the length of the vector. So x of 1 is 2, similarly x of 2 is 3, similarly x of 4 is 5, and if I type in x of 5, it yields another error that index exceeds the array bounds. So we cannot exceed the array bounds here in case of MATLAB, because x only has 4 elements. The fifth element is not there. So if you want to um, see which variables you have already created, you can type who, and it gives you the list of different variables that you have created so far. This x, a, and s, and you can also verify them here from the workspace. You can see these variables are specified here. Now if you want to have more details regarding these variables, you can write who s. Okay, so it gives you some more information related to these variables, the size of these variables, similarly the number of bytes each of these variable takes, and the class. I've not talked about the class of these. There are different classes provided by MATLAB. They specify the size in bytes of that a variable can take if it is of a specific class. So if you want to know more about this, what type of classes does MATLAB support, we can type in help class, and it gives us some of these the names of the different classes that MATLAB supports, and along with the size of each of the elements of that. So we can have double, so double precision floating point number array. This is the traditional MATLAB matrix or an array. Single precision floating point numbers. Logical values, scalars, or arrays. Char, it's a character array. Cell array, we'll talk about that later. You can design a structure, function handle. You have int 8, that means 8-bit signed integer array. Not specifically an array. You can design a scalar as well, but a scalar can be considered to be as a 1x1 array. So the word or the term array here is generalized, so we can consider every variable that we create in MATLAB as an array or as a matrix. uint 8, unsigned integer. Each value takes 8 bits. Similarly, 16-bit integer. Each value here in that array would take 16 bits. Unsigned 16-bit integer. Similarly, we have 32-bit integer signed and unsigned 32-bit integer. We have a 64-bit integer. We have an unsigned 64-bit integer, and so on and so forth. So we can remember these types, and if you want to convert one variable into another, we can typecast values from one class to another, just like this. So let's suppose if I say x is equal to 6, and I want to see which class has MATLAB assigned to it automatically. I'll write who s x, and it specifies. So it specifies the name of the variable, the size of this variable in terms of the dimensions, the number of bytes it takes, and the class. So this variable x has been assigned the class double by MATLAB. If you want this to be an integer, let's suppose an unsigned 8-bit integer, you can write x is equal to uint 8 of x. So we have converted this x into a unsigned 8-bit integer, and if we write who s x, it says that it takes 1 byte. Okay, the class is uint 8. The size remains the same, and the value also does not change in this case because it was not required. So that's how you can move across these classes depending upon your requirements. If you want to define a variable to be a double, an integer, or a character, and so on and so forth. So we have already declared, so let's redeclare it in fact. So x will declare a vector using these square brackets. So x is equal to 4, 5, 6, 7. So it has 4 elements, and if I write who s, it gives me, sorry, if I write who s x, it gives me all the details about this, because it considers each of these it has assigned the class double to this variable x, and there are 4 elements, and each element takes 8 bytes. So the total number of bytes taken by x is 32. So if we convert this vector to uint 8 again, we'll write x is equal to uint 8 of x. So if I write who sx, the size remains the same, the dimensions are the same, the bytes have changed because now each of the elements in this vector takes only a single byte, so the total number of bytes is 4 in the class. Since we have typecasted it to uint 8, it is uint 8. Now I've already shown you how to access the elements. So x of 1 gives us the first element, similarly x of 2 or x of 3 gives us the second element, and so on and so forth. It also gives us the type of that particular element. Now there is a special operator which is this colon, and it is used to access a range of indices from a vector. So if I write x of this colon, it means all rows, all columns. Okay. Now in this case, this so I've asked MATLAB to display all rows and all columns in this case. So if I write x of 1 to 2, so it gives me, let's first see what x contains. So x contains 4, 5, 6, and 7. So it's a row vector. Okay. Now if I write x of 1 to 2, this colon here means 2, the range 1 to 2. So it gives me all the values pointed to by x of 1 and x of 2. So 4 and 5. If I write x of 1, 2, 3, so it will give me the first 3 values of this vector 1 to 3. I can also write x of 2 to 3. So it gives me this sub vector. Similarly, I can write 2 to 4. Again, you want to see what's in x. So 2 to 4 gives 5, 6, and 7. As I said, that indices start from 1. Now you can write something like this: 1 to 4, but you may specify a different step. Earlier the default step was 1. If I write 2, so what it displays is, if you look at this vector, original vector, it's 4, 5, 6, and 7. Now I've asked MATLAB to display x ranging from 1 to 4, but with a step of 2. So it will first display this x of 1, that's what it has shown here, which is 4 in this case. Then it will increment the counter by 2. So 2 plus 1 is 3. So it will display the third element, 1, 2, and 3, so which is 6. So that's what it has shown here. Now the current index is 3. It will now again add that particular counter by 2. So 3 plus 2 becomes 5, but we have only 4 elements in this vector. Okay, so it does not display any other or any further elements in that particular vector because we have only 4 elements here. So that's how we access elements from vector. Now let's talk about some of the functions that are available in MATLAB for handling or manipulating these vectors. The first of them, let's clear the screen first. So x, in this case, we have already defined a vector. Now you can see that x here is a 1 cross 4 row vector. Now if you want to convert this into a column vector, you can simply use an operator known as the transpose operator. X transpose, this tick there. So it converts this row vector into a column vector. Now the accessing the elements remains the same, though the indices do not change in this case. We'll later on see how, in case of matrices, how it changes a little bit. we have to convert subscripts to indices and indices to subscripts. We'll see that later on. Now let's continue with some of the functions which are available in MATLAB for dealing with these vectors. So let's talk about the first one, max. Max is, as the name suggests, it gives you the maximum value from a vector. So max of x is 7, as is obvious here. 7 is the largest number in this vector x. Similarly, min of x gives the minimum value. Now the length of x gives the total number of elements in this vector x. So the total number of elements in this vector x is 4. Now if you want to sort a vector, so sort x. Now in our case, the vector was already sorted in non decreasing order. Now if you want it, to sort this vector in a non-increasing order, you will have to use some additional parameters to the sort function. So sort x in descending, DESC. Okay, so you can see the output. I've passed this parameter DESC. It's another parameter for this sort. Sort may have more parameters. In order to have a good understanding of each of the functions, you can always type help and the name of the function. So I've done that, and gives you the manual or the reference for this function. So it gives all the possibilities of using the sort. So sort A, if A is a matrix, you can specify the dimensions along which it should sort this. We are right now not talking about matrices. We are considering only vectors. Similarly, we can have sort A and the direction. The direction could be ASCND or DESCND. In fact, it performs some kind of a pattern matching, and since I've not written the spelling correctly, but it's still taken this to be DESC. So DESCEND descent again gives you the same result. So you can go through these manuals of each of these functions to get a more better understanding of how they function, what they work, how they work. So I'll talk about some other functions in this case. So this sum of the elements of a vector, x is in this case is our vector, so it's 22. X was 4, 5, 6, and 7. You can verify whether the sum is right or not. Now the prod is another function. It gives the product of the elements of a vector x. So 840 is in this case is the result of this function applied on vector x. Now we can find the median of x. I hope you know how to calculate the median. This function gives you the median. In this case, it's the n plus 1 divided by 2th element after sorting it, obviously. So mean is there. Mean of x in this case is 5.5. We also have the standard deviation of x of any vector. So this STD works only with this double, these class variables. So we can convert back x in our case, as you might remember, is we typecast it to uint8. So we'll write who s x, it's uint8. Let's convert it back to double. So x is equal to double x. Okay, now who s x, now it is double, and let's try to see if the function works. STD of x, so standard deviation gives you the standard deviation of the elements of x. So you can always use these scalars, vectors, and these functions to perform all the required computations that you may want depending upon your problem. Now let's try and deal with some matrices. Now, as I earlier talked about, this a single vector, or let's suppose a single value, a scalar value, let's suppose y is equal to 3, can be considered to be a 1 cross 1 matrix. Similarly, the vector that we earlier designed, created, this 1 cross 4 vector, okay, this 4 element vector can be considered to be a 1 cross 4 matrix. Okay, so you can generalize your view of these variables in MATLAB to be matrices, and there are some there's a specific way of defining matrices as well. So let's say M1 is the name of the matrix that we are going to create. So this square bracket is used to define these matrices. The first row of the matrix, I'll write something like 2, 4, 5, 6. Okay, now in order to start the second row, I'll use this semicolon operator here, and then write this, maybe the second row of my matrix, 5, 4, 1, 2, and 5. It's important that the number of elements in the first row and the second row should be the same, otherwise it will throw an error. We'll see that later. So I want to design or add another row to this matrix, 3, 6, 7, and 2. Now if I type enter, you can see that this becomes a 2 cross 4 matrix, 2 rows and 4 columns. So an alternative way of defining this matrix would be using the commas as well, but using commas is recommended, because that way it becomes a little clear. The elements are more kind of visible, so gives you this syntax gives you the same result, same matrix here. Okay, now you might remember that transpose operator. If I apply the transpose on M1 transposed, the rows convert into columns, the columns convert into rows. It becomes a 4 cross 1 matrix, and the elements are accordingly transferred. Now we have designed our first matrix, and we call it M1. M1 is the matrix. It is a 2 cross 4 matrix, and these are some of the elements. Now let's try to apply some of the scalar functions on this matrix and see how whether they do work on a matrix or not, and if they do, how. Is there any kind of a difference? Because earlier we were applying scalar functions on scalar values and there was no problem, but right now we have matrices. We have a matrix, and we'll see how it works on it. So let's talk about this. So let's consider the sine function in this case, sine of M1. So what should it do? It's obvious that sine of a matrix can only be calculated in terms of its individual elements, and that's what this function would do. Sine of M1 would give you the same. M1 is a matrix here. It would give you the output of this operation would be the matrix of the same size as that of the input matrix, and each of the elements here would be sine of the respective element in the input matrix. So 0.9093 is the sine value of this 2. Similarly, this minus 0.7568 is the sine value of 4, and so on and so forth. So scalar functions, when applied to matrices, apply on individual elements of that particular matrix. Same applies to vectors as well. If we apply a scalar function on a vector, it will apply on each of the individual elements of that particular vector. So similarly, let's suppose we have this let's try and add some value to this matrix, and let's try to see how operators work on matrices. So if I write M1 plus 2, now plus 2. Now, M1 here is a matrix, and this 2 here is a scalar. How can we add a matrix and a scalar? Now, if you see the output, this is the original matrix, and this is the matrix after we have added 2 to this particular matrix. So this it's obvious that each of the elements of the input matrix were added with this 2. So as you can see here, 5 becomes 7, 6 becomes 8, 5 becomes 7, 6 becomes 8, 3 becomes 5, and so on and so forth. So any of the operators, similarly, for example, if I write multiply m1 by 2, so it multiplies each of the elements of the input array, input matrix in fact, with that scalar value that we just specified. So similarly, if I write cap, it raises each of the elements in m1 to the power of 2. Let's see whether it does or not. Now, this is where the problem comes in. Earlier, I told you that there is a difference of applying these operators to matrices and scalars. Now, in this case, m1 here is a matrix, and 2 here is a scalar. Okay, so there's a kind of a mismatch between the types of these values here. So in order to perform an element-wise operation, we have to write m1 dot and that operator. So dot prefix here before any of the operators simply tells MATLAB to perform an element-wise operation and not a matrix operation. Okay, because this would mean m1 raised to power 2 in this case would mean m1 multiplied by m1, and this multiplication is matrix multiplication. And if you look at this matrix, it is a 3 cross 4 matrix multiplied by a 3 cross 4 matrix. It obviously is a dimension mismatch. So this won't work. This m1 multiplied by m1 would perform a matrix multiplication, and in this case it throws an error. As you can see here, it throws an error because the dimensions of m1 and m1 in this case are not compatible for multiplication. However, this would work if I write m1 multiplied by m1 transpose. It would be a 3 cross 4 matrix multiplied by a 4 cross 3 matrix. Then it would work. As you can see here, the output is a 3 cross 3 matrix in this case. So if you want to specify to MATLAB that the operation that you are applying on a matrix has to be an element-wise operation, you have to precede your operator by a dot. So let's see. So if I write m1 multiplied by m1, it throws an error because the dimensions do not agree. If I write m1 dot multiplied by m1, it tells MATLAB to perform element-wise operation. So the first element of m1 would be multiplied by the first element of m1. Similarly, the second element of m1 would be multiplied by and so on and so forth. So if we see this m1 here is this matrix. So 2 into 2 would be 4, 4 into 4 would be 16, 5 into 5 would be 25, and so on and so forth. So this is how you differentiate between a matrix operation and an array operation. So this here is an array or element-wise operation. Okay, so we were trying to manipulate or perform operations between a matrix and a scalar. So again, we'll revisit it. M1 dot multiplied by 2 would give you the same result as M1 dot multiplied by 2 because it does not consider this to be a matrix operation. But if you write cap, it treats this operation as M1 into M1, which would throw an error. So I have to specify to MATLAB that you do not need to perform a matrix multiplication in this case, or the matrix raised to power. You have to perform a scalar, element wise raised to power. So dot precedes here this cap operator, so it raises each of the elements to the power 2. Okay, so this is all about some of the operators. We'll talk about the forward division and the backward division, the left and the right division later on in case of matrices. Let's try and apply some functions on some other functions on this on a matrix. So if I write, for example, these would be the scalar functions. So if I write cos of m1, again it performs a an element-wise operation. So cos of 4 is minus this, and so on so forth. Sorry, not 4. Actually, m1 is this 2. So this is cos of 2. This would be cos of 4. So this would be cos of 5, and so on and so forth. Now let's try and apply some vector functions on matrices and see how they perform, how they work, what output do they give. So if I write max of m1, the output of this operation applying a vector function on a matrix, on a two-dimensional vector, a two-dimensional array, also yields a vector. Now we'll have to kind of a little bit investigate as to how it happens. So let's first revisit how max applies on a vector. So let's suppose I'll create a vector vec1 is equal to 2, 4, 5, 6 and 6 and 7. Okay, and I apply max on this, max of vec1. Okay, so it gives me 7. So in this vector, 7 is the largest element. That's okay. But if I apply this max on m1, on this matrix m1 here is this matrix here. Max of m1 does not give me a single element, but it gives me multiple elements, and I'll have to see what this basically means. Now, if you look at this column here, this is the first column of matrix 1. It contains 2, 4, and 3. Now, this max does not apply on the matrix completely. It applies on individual vectors, and each of the vectors in this case is taken to be a column vector. Okay, so max of this column vector is 4, and max of this column vector is 6. So we write 6 here. Max of this column vector here is 7, and similarly max of this column vector here is 6. So when we apply vector functions on matrices, they apply column wise. We can simply infer that. Similarly, if you apply sort on m1, so it sorts these vectors. If you look at these vectors, these column vectors, so 2, 3, 4 will be given here. 2, 4, 3 will be converted to 2, 3, 4. 4, 1, 6 will be converted to 1, 4, 6. Similarly, 5, 2, 7, 2, 5, 7, and so on and so forth. So similar to the vectors, we'll try to see how. Okay, so similar to the vectors, we'll try to see how to access elements of a matrix. Now, the idea is using the same syntax. If M1 is a matrix, we'll use parentheses to access the elements. If I write M of 1, okay, the first element of M1 is 2. Okay, we'll see how it translates. Now, if I want to see the second element of M1, it gives me 4. Okay. Now I'll have to first see which the actual matrix M1. So M1 is this matrix here, and if I want to write M1 of 1, it gives me 2. M1 of 2 gives me 4. M1 of 3 gives me 3. M1 of 4 gives me 4. We'll see how translates to. So M1, the first element of this matrix is 2, as can be seen here. Similarly, the second element of M1 is 4. Now we are not sure whether it's this element or this element. Now the third element of M1 is 3, okay, which is this here. Now it gives us a hint that the matrices in MATLAB are stored in column major form. Means first this column will be stored, sorry, this particular column will be stored, then this column would be stored, similarly this column would be stored, similarly this column would be stored, and so on and so forth. It means that this would be 3, 6, 9, and the 10th element of this matrix M1 would be 6. Let's try to find out. The 10th element is 6. Similarly, if we look at let's review this M1. The 7th element, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9th element would be 7. Let's try to verify it. The ninth element is 7. Okay, so it's obvious that that MATLAB stores matrices in column measure form, and that's how you get the indices of each of these elements. Now there is another way of accessing the elements of a matrix in MATLAB, and that's using subscripts. Now subscripts are two element pairs which specify the row number and the column number of an element that you want to access. So let's suppose for this one, we can see it belongs to row number 1 and column number 1. So we can access this element m1 as m1 of row number 2 and column number 2, 2 comma 2. So this is the row number and this is the column number. If I write enter, it gives me 1. So similarly, this is 3 comma 4. So third row and fourth column would be 2. So third row and fourth column would be 2. Now there is a function called sub to mat and mat to sub, which can be the function is index to subscript, and this other function, the counterpart, is subscript to index. So they help you to convert an index into a subscript and a subscript into an index. You can explore that yourself, these functions. Now you can extract you can specify a range of elements, as we did in a vector. For example, if I write m1 of all rows, colon here means all rows, and column number 5. Okay, so this colon here means all rows, and the second subscript is the column number, which is column number 5. So it should give me, in fact there is no column number 5, let's suppose column number 3. So it should give me this column here, 5, 2 and 7. That's what it gives, 5, 2 and 7. So let's review the matrix M1 and type in this M1 of rows 1, 2, 3 and column number 2. This means rows from 1 to 3, so 1, 2 and 3, and column number 2 only. So it means this 4, 1 and 6 would be visible. So 4, 1, 6. Similarly, you can write, for example, rows from 2 to 3, which is basically this row only. The row number 2nd and row number 3rd, to row number 3rd in fact, and column numbers 2 to 4. Okay, so it gives me this sub matrix here. This sub matrix in here. Rows from 2 to 3, which is these two rows, and columns from 2 to 4 only, and this 2 to 4, and this is the submatrix which is visible here. You can save this submatrix in some other variable and use that variable later on. Let's suppose I is equal to m1 of 1 to 4 and comma 6. Sorry, 6 is not there. 3 and column number 3. So sorry, 4 is not there. So 1 to 2 and 3. So this gives you this area here. These two elements, 5 and 2. Rows 1 to 2, rows 1 and rows up to 2, and column number 3. Now again we could specify a different step like we did earlier. So rows 1 to 3 and columns from 1 to 4, but with the step of let's suppose 3, with the step of 3. Okay, so with the step of 3, let's see what it gives us. It gives us let's first view what M1 contains. M1 contains this. M1 is this matrix here. So M1 of rows from 1 to 3. So rows from 1 to 3 means 1, 2 and 1, 1, 2 and 3. Okay, these are the 3 rows, and columns from 1 to 4, but with the step of 3. So it should give us this. It should give us this row, first row, second row, third row. Okay, but the column numbers would be from 1 to 4 with a step of 3. 1 would be the first column, then it would increment this 1 by 3, which means 4, and this would be that second column that would be displayed. Okay, and the next increment would exceed the bounds that it want continue with that. So this would give us the first column and the fourth column. Similarly, rewrite it. Let's do something like this. the row number 1, okay, elements from row number 1, but which columns? From 1 to 4 with a step of 3. So 1 would be 2, okay, then 1 would be incremented by 3, which would become 4, so, and this element would be displayed this 6 here, and after that it would exceed the bounds and not display anymore. So 2 and 6 would be displayed. It is this 2 and this 6. I hope this is clear. You can work around yourself and see how it works. So let's continue rest of the things later on. Till then, thank you.